The goal for today is to talk a little bit about radius of convergence. Now, I don't want you to get too caught up in the details, because the details are not the important thing. Basically, we have to remember that when we're dealing with series, that there's always the question of when does this make sense? Now, for polynomials, where we stop at some point, it always makes sense. But for series, it gets a little bit more delicate. And so we can talk about, well, where does it converge? And it turns out that when we're dealing with series of the form some constants x to the k, that there will be what we call a radius of convergence. So in other words, it will converge inside a circle in the complex plane. Now, how does one find it? Well, you can find it by taking the limit of the ratio of the coefficients. This gets back to ideas from Calculus 2. Again, let's not get caught up on the details. Mostly the mindset here is, hey, there are limitations to series answers. And by that we mean it's possible that we can come up with an answer which works for sort of a narrow window, whereas if we use a different technique, it actually works more broadly. And we'll see an example of that today. So for now, mostly we're just going to do some very simple examples showing how we can use series to find complete solutions, which, in other words, they're not going to be very hard differential equations, but this just says, let's put some, rubber to the road, so to speak. Let's see how it works. So our first example, we're asked to solve y prime equals 3y with an initial condition y of 0 equals 1. And we're going to do it in two different ways. Namely, we're going to do it by separable ODE. In other words, what we would have done before we talked about series. Then we're going to do it by use of series. And then we'll ask the question, are these the same? All right. Well, let's take a look and see what we have. So first off, let's do the separable ODE. And that shouldn't take too much space. So you think of y prime as dy dx. So we have dy dx equals 3y. Well, that's the same as dy divided by y is 3 dx. All right, well, that's integrating both sides. Log of y is 3x plus c, right? So we should mark that we integrated, so we'll put some integral signs here. Integral sign, there we go. Now we want to solve for y, so we take the exponent of both sides, and that would give us that y is some constant e to the 3x. Remember, this constant is not quite that constant. So really what we'd have is e to the 3x plus the upstairs, which is e to the 3x times e to the c. And you say, we'll just rename e to the c as your new c. This is going back to our constants are sponges. They absorb other constants. Now that's the general form. We do have an initial condition. So we apply our initial condition. We say, okay, well, y of 0 equals 1. That tells us that 1 equals c e to the 0, or c equals 1. And so we come to the conclusion that our solution using our separable ODE is y equals e to the 3x. All right, so we've solved it. So now we know it is solvable. Let's go to 2. And this says, all right, do it by use of a power series. Okay, so now what does that tell us? Well, it tells us that, all right, so this is number 2, just making it clear. I guess we should have put here, this is number 1, so that we'll have that for our notes. And what do we see? Well, we're going to write y as a summation c k x to the k, where we go from 0 to infinity. So a big polynomial. And now we're going to put that into both sides. So we say, okay, so the sum k equals 0 to infinity, ck x to the k prime, okay, so that's our y prime, is equal to 3 sum k equals 0 to infinity, ck x to the k. Y prime equals 3y. All right, well, this becomes the sum k equals 0 to infinity of k ck x to the k minus 1. And that's equal to, well, here we'll have the sum k equals 0 to infinity, 3 ck x to the k. Now, I want to compare, but it's a little bit strange here, because notice here I have x to the k minus 1, here I have x to the k. So I'm going to do a quick shift, right? So if we shift, then everything will look the same. And one other thing to note is what happens when you plug in 0 on this left-hand side. Well, if you plug in 0, you'll get 0 times stuff, which is 0. So we can actually change this to a 1. And we're going to do a quick shift, L equals K minus 1. Here we won't do any shift, but I just want to make it look the same so that it's easier to make comparisons. So when we do this shift, what do we have? Well, we have a sum. Now, we start at 1, but K minus 1 is 0, so L equals 0 to infinity. K, well, that's L plus 1. And then C sub L plus 1, x to the L. Now, that's equal to our sum. Now, on this side, we just copy it, but everywhere where we see a K, we put an L. All right. Now, what's true? Well, what's true is I have big polynomial equals big polynomial, right? Yeah, I do. And now, that's what we have when we have series, big polynomial, big polynomial. So coefficients have to match. And so our great aha is to say, okay, well, this has to match that. So we now can say the following. We can say that for L greater than or equal to 0, we have that L plus 1 times C L plus 1 is equal to 3CL. Or, put another way, we have CL plus 1 is equal to 3C sub L over L plus 1. Now, where do we start? Right? Now, this just tells us how we recurse, but how do we know what our first value is? That's where initial conditions come in. So, looking at our initial conditions, we say, we have y of 0 equals 1. Y of 0 equals 1 tells us the following, namely, it tells us that C0 equals 1. So, now we're good to go. Okay, so let's start writing down terms. And when we're writing down terms here, we're looking for patterns. So how do you find patterns? Well, piece of advice is if you're looking for patterns, don't try to simplify. Oftentimes, simplifying is obfuscating when you're looking for patterns. And so you want to keep everything there and avoid cancellation, because cancellation might obscure what is happening with your patterns. Okay, so C0 equals 1. Let's start with our C1. That would be L equals 0. So that would be 3. C0 is 1. So we'll say times 1. And then here we're doing L equals 0. So 3 over 1 times 1. All right, how about C2? Well, that would be 3 over 2 times C1. 3 over 1. And then times 1. All right, how about C3? All right, that would be coming here. So that would be see, I want L plus 1 to be 3. So it's 3 over 3 times 3 over 2 times 3 over 1 times 1. How about C4? Well, that's L plus 1 is 4. So that would be 3 over 4, 3 over 3, 3 over 2, 3 over 1 times 1. Now you might say, wait, where did all that come from? All of that is C3. And now at this point we're like, ooh, there's a pattern here. So in general, CK is, well, 3 over K, 3 over K minus 1, down to 3 over 2, and 3 over 1. What do we have? Well, upstairs there's a bunch of 3's. So we say that's 3 to the K. Downstairs, K minus 1, 2 times 1. That's K factorial. All right, so our great aha. Here we go. We have our series solution. We figured out what our pattern is for our CK. So we put that in to our form. So we say that our answer is y is the summation k equals 0 to infinity of 3 to the k over k factorial x to the k. All right. Good. Good. So we've done both. All right. And now the question, are these the same? And you might say, they don't look the same. How could they be the same? Well, we start going through our old notes and we say, you know, there's this fun fact. E to the something is equal to the summation k equals 0 to infinity of whatever that thing is to the k over k factorial. And of course, there's always the age-old question, what's in the box? What's in the box? Right? And so we say, okay, what would fit here? Because we do think that we have e to the 3x, so we should think, okay, it should look like that. So let's actually start with this. So we have e to the 3x. Let's plug it in and see what we get. So we would say, okay, so e to the 3x, what is that? Well, that's the summation, k equals 0 to infinity. You put 3x in the box. 3x to the k over k factorial. Now what we can do is 3x to the power of k. That's like 3 to the k times x to the k. So that's the summation, k equals 0 to infinity of 3 to the k over k factorial x to the k. And now we're like, what? Okay, we see that this was our answer to number 1, this was our answer to number 2, and they're equal. Now you might say, well, wait, is it always equal? Yes, because this relationship is true for whatever you put in the box. And so, in other words, the radius of convergence is infinite. And so, they are the same. All right, so this is sort of what you might call proof of concept. We are able to take a problem and solve it using old techniques, and then solve it using our series techniques, and we get the same answer. This shows that, hey, we could actually make this work when we can't solve it with old techniques. So that's good news for us. Yay, us! All right, well, let's try another problem. So in this problem, we're asked to solve x plus 4 y prime plus y equals 0 with y of 0 equals 1 by use of a power series. Okay, so we'll do that, and then there's some other things we're going to need to do: determine the radius of convergence of the answer and compare the answer to what we can find by other methods. Okay. All right. Well, let's start. So we'll go in order. So solve x plus 4 y prime plus y equals 0 by use of power series. Well, so what does that say? We start off by saying our answer is going to look like the summation k equals 0 to infinity of ck x to the k. Now, we're going to take this x plus 4y prime, we're going to actually expand it. So we're going to say, all right, we're going to take our x, y prime, so that's summation k equals 0 to infinity, and we'll go ahead and take k, ck x to the k minus 1, plus 4 y prime, sum k equals 0 to infinity of k ck x to the k minus 1, plus y, which is the sum k equals 0 to infinity of c sub k x to the k, set it to 0. Now you might say, why did you do that? In other words, why is it that we took this and we said, oh, it's xy prime plus 4y prime plus y? Well, the thing is, we don't want to multiply the x plus 4 into the series. That's not going to help us. The problem is when you multiply x plus 4 into the series is it's going to have x plus 4 times x to the k minus 1. You're going to have 2 powers of x in that series. You don't want that. You want every series to just have a single power of x. So if you see expressions like this, you say, okay, just multiply out and handle them separately. All right, well, now we're going to, do some work, right? We're going to be patient. We aren't in a rush. We're going to enjoy our time here. All right, so in this case, we'll multiply the x in. So we have the sum, k equals 0 to infinity, k c sub k x to k, plus here we can multiply the 4 in. Yeah, sure, why not? 0 to infinity, 4k ck x to k minus 1, and plus summation k equals 0 to infinity of ck x to the k. All right, good, good. Now, we go into our mantra, which is we're going to shift first, peel if needed, combine. Peel, shift, combine. Those are our 3 steps. And so we say, okay, do we need to shift? Well, we check our powers. X to k, x to k minus 1, x to k. Okay, they're not agreeing. They're different, right? So we say, okay, so let's do our shifts. Now, some of these are going to be easy shifts. So here, k equals L, and here, k equals L. Now here, we're going to have k minus 1 to be L. All right, so the first sum becomes L equals 0 to infinity, L c sub L x to the L. In other words, there's not much to do. And same with the last sum. All we're doing with the first and the last is we're just saying, hey, let's rewrite and put k replaced by L. Now in the middle one, something interesting will happen. So when k is equal to 0, what do we have? Well, we'd have L would be minus 1, right? 0 minus 1 is minus 1. So minus 1 to infinity. All right, then we'd have 4. Now k is L plus 1, c L x to the L. Now at this point you're like, minus 1, that's not looking good. Do we need it? Let's think about that. What happens when you plug in minus 1? You'd have 4 times 0. As soon as you get a 0, it doesn't matter what anything else is. So you say, actually, we can ignore minus 1. Essentially what we're doing is we really are peeling off, but we're peeling off 0, and so we're saying, okay, great. We just start at 0. So we could count this as a peel. So there's no cheating. I want you to know that. We're not going to cheat. That's not how we roll. That's not our jam. All right, well, now we're like, nice. All our starts align. Okay, so since our starts have aligned, we can now combine one sum. All right, of course, I say that, but I noticed I made a mistake, and you probably saw my mistake too. I updated the L plus 1 here. I updated it here. I didn't update it there. Okay, so let's fix that. This isn't C sub L. This is CL plus 1. So don't make the same mistake I made, which is to say, make sure you account for every K. All right, well, now that we've fixed that problem, all right, into a single sum we go. So we have our sum, one sum, 0 to infinity. Okay, well, we have an LCL and then a CL. So if we take those two together, we can write that as L plus 1 CL. Okay, that's those two terms together. And then we have plus, here we'll have 4 L plus 1 CL plus 1. And that's x to the L, and we want that to equal 0. Okay. Well, now let's give ourselves a little bit of space here. What can we conclude? Our great conclusion is this coefficient always has to be 0 because it has to match the right-hand side. So that gives us information. And actually, we can go even further, right? So let's write this down. We have 4L greater than or equal to 0. Now, how do we know it's for L greater than or equal to 0? It's where the sum starts. So we're going from 0 on up. We have L plus 1 CL plus 4L plus 1 CL plus 1 equals 0. Now, we can divide out by an L plus 1. Why can we do that? It can never be 0. In order for L plus 1 to be 0, L would have to be negative 1. So we're like, oh, well, that's great. So we get C L plus 1 times 4 plus CL equals 0. Or, okay, move it across, divide, C L plus 1 is minus 1/4 CL. All right, good, good. Now we're ready. What's our pattern? Well, our pattern is going to be pretty simple, right? It just says for the next coefficient, multiply by minus 1/4. But where do you start? Well, that's the initial conditions. Initial conditions are going to tell us how we start. We know that our y of 0 is C0, which is 1. So C1 is negative 1/4 times 1, because you multiply by negative 1/4. C2 is negative 1/4 times C1, negative 1/4. C3, negative 1/4 times C2. And it's, as I said, in general, CK is negative 1/4 to the power K. So this has an easy to spot pattern. All right, good, good. Now, what can we say? Well, now that we have our answer, we can now say the following, and that is, we get our series solution, y, which is our sum, k equals 0 to infinity, ck x to the k. Well, that's the sum, k equals 0 to infinity, of minus 1/4 to the k, x to the k, which we can write it as the sum k equals 0 to infinity of minus x over 4 to the power k. And there we go. There's our answer. We found it. All right. Cool. Cool, 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 cool. Of course, that's just the first part. Okay. Determine the radius of convergence of the answer. Now, we're in luck, right? Because let's go back. And we're going to make a note here. You take the ratio of the current coefficient over the next coefficient in absolute value. Now the thing is, using our recurrence relationship, that's going to be pretty easy. All right, so what we have is we get that our radius of convergence, so rho, is our limit, as n goes to infinity, of Cn over Cn plus 1. Well, we know what the Cn's look like. So this is our limit as n goes to infinity. Well, okay, so it's negative 1/4 to the n over negative 1/4 to the n plus 1. Running out of space. But, okay, this becomes a negative 1/4 downstairs, which becomes a negative 4. You take the absolute value. This becomes the limit as n goes to infinity of 4. Well, that's a pretty easy limit to take. It's 4. All right, so this is our radius of convergence. So, in other words, this only makes sense as long as we don't go too far away from 4. Sorry, from 0. We can go up to 4 away from 0, and then it's like, well, you give up. All right, now we have a little bit of space, and we still have more to answer. Compare the answer to what we can find by other means. You know, let's not try to cram too much in here. I'm going to grab another piece of paper, and give me a second here. I found it. Okay, so I'm going to cover this up. And this is, I want to keep that for reference. So, let's solve this equation by another way. Well, is there another way we could solve this differential equation? And the answer is yes. We can solve this by separable. So, we can rewrite this as x plus 4 dy dx equals negative y, or we could say dy over y is equal to minus 1 over x plus 4 dx. All right, so now what do we do? Well, we're going to integrate both sides. So, and what does that give us? Well, it gives us the following. Log of y is negative log of x plus 4 plus c. Well, this negative in front can go in as an exponent. So this is the same as log of x plus 4 to the negative 1 plus c. And taking both sides, put it into the exponential function, we end up with y is equal to some constant c over x plus 4. All right. Now, what's our constant? Well, that's where we use our initial conditions. So we know y of 0 is 1. Okay, so y of 0 equals 1. Well, that gives us that y of 0 equals 1 equals c over 0 plus 4. And so, what is that? Well, that tells us that c equals 4. So y is equal to 4 over x plus 4. Okay, so that's our solution found by another method. Y equals 4 over x plus 4. So maybe we'll make some notes here. Other method. Y is equal to 4 over x plus 4. All right. Now, coming back here, say, okay, great. Are these the same? Well, are they? Okay, let's come back and let's see, can we get a little bit more space here? There we go. So I just want to make sure we can see our solution we found. These are our solutions. Are they the same? Okay, let's be careful here. So, when is this true? When do we have y equals 4 over x plus 4? When is that valid? Well, if you graph this, we have an asymptote over at x equals negative 4. And so what's going to happen is that you're going to pass through y0 equals 1, and then you're going to go up to that asymptote, and then otherwise you're going to go down. So when does this hold? Well, this will hold, it's valid, above negative 4. Now, you can't go below negative 4. Remember, solutions cannot pass through asymptotes, because in order for me to get to below negative 4, I have to be able to follow the line. And in other words, I have to be able to never lift my pen. But at negative 4, I'm definitely doing a pen lift. Okay, so this is valid for x greater than negative 4. Okay, so again, we'll copy it here. This is valid for x greater than negative 4. Now, let's come back to this one. We talked about the radius of convergence. So, what's the radius of convergence tell us? It tells us that as long as we're within 4. So this solution here, this is valid for negative 4 less than x less than positive 4. So here's the thing. Are these two the same? Yes and no. Yes, in between negative 4 and positive 4, no in general, because this holds over a larger range of x. So it does show that there are limitations to power series solutions. So sometimes things which are true are only true for a narrow window, but if you had a better solution, you could extend it to a bigger window. Well, okay, that's all right. At least you have something. So I don't want you to walk away saying, series solutions, these are no good. We can't use them. You can. They're perfectly fine. Don't stress about it. Oftentimes, it's good enough to say what happens nearby. That's the whole theme of calculus. And really, differential equations is just sort of calculus with some extra steps. It's good enough to say what happens nearby. And nearby, they'll line up. All right, well, great. And you might say, we got lucky here for our radius of convergence. Is there a better way to do that? There is, at least in some cases, and we'll talk about that next time. But for now, we're done. So, see you again. Bye.